Whoa, that's my bad. Okay. Yeah, I'll just leave it up here, Xiaopeng, and you can introduce, and then when you're done, I'll switch to the PowerPoint.
Yes, thank you. I will give you a cue. Is there some echo? Hello?
Can hear you.
Hi, Nancy, are we on?
We are.
All right, cool. Good afternoon, everybody. This is the beginning of what should be an exciting series on big data machine learning in hydrology. I'm your host here, Chapon Shem from Water Resources Engineering at Penn State University. This series is intended to bring out some contributions to big data machine learning in the most recent year or two. Let's see, some echoing. All right, that seems to be better now. Sorry. In the most, this series is intended to bring out some notable contributions to big data machine learning in the most recent year or two. In the last year, interesting. Does somebody have cell phone?
It should be the case that only the staff can talk. So maybe if Alex, Freddie, and Ansley check their mute themselves.
All right, sorry for the interruption, folks. In hydrology, the introduction of big data machine learning has substantially enhanced our ability to address existing challenges and encouraged novel and new applications. Now, because this field is very large and is also growing very rapidly, it's really a very small selection of the many potential works that could be introduced, and I expect there to be more. So today we will begin with Dr. Gray Nearing, assistant professor from University of Alabama. Gray obtained his PhD from University of Arizona hydrology program, I believe with Bhushan Gupta. I first noticed Gray's work 2 to 3 years ago when he attributed uncertainty to different sources using information theory. And I also noted sometimes his philosophical discussion in many different occasions. So some of these methods tried to gain more in-depth understanding of model processes and deficiencies. So today his topic would be along this line, to benchmark and diagnose models using information theory. This should be an interesting talk, so without much ado, we'll get started with Gray.
Great. Thanks. Oh. All right. So let me know if you can't hear me. I don't have any feedback since I'm presenting, so one of the other organizers will have to let me know if someone chats. Feel free to jump in and block and interrupt. Basically, I've worked for a long time with information theory, and we've used machine learning as a tool to help understand the relationship between observation data and process-based models. The big story here is that I think that moving forward, we're at a tipping point. I've been working with machine learning in hydrology for about 10 years now, and I've noticed a big change in the conversation. AGU this year was from my perspective, surprisingly different than it's been in the past. Almost everybody was aware of and using machine learning in some sense. And in the past, in the previous years, we've had some resistance to machine learning being non-physical, and that's within the span of something like 18 months in our field. I think that sentiment has maybe not gone away completely, but it's much less than it used to be. I think we're at a tipping point, and I think we should be aware of what that means for hydrology as a science. And hydrology, again, it's just a canary in the coal mine. I think that most fields of science are having this discussion right now. And the discussion that I'm talking about is about the relationships between the relationship between physics and statistics. So what's the difference between physics and database learning, and how do we extract the maximum amount of information from both of these tools that we have at our disposal. Just to give some credit where it's due, most of this work that I'm doing comes out of efforts that I've done in collaboration with other people interested mostly in information theory. I got into this because I was interested in information theory, and the machine learning became a tool to do some of the model diagnostic stuff that we wanted to do. We've had 2 workshops on information theory recently, one in 2016 in Germany and one in 2018 in Spain. And so this is sort of a group shot of the people that have been involved in that. I specifically collaborate with Ben Ruddle and Hoshin Gupta and Praveen Kumar and Stephen Ways and other people like that. So I just want to give some credit to where these ideas are coming from. And I also want to just plug our information theory and the earth science summer school this summer 2019 in Santander, which should be really interesting. So if you're interested in that, there's an advertisement on the CUAHSI webpage. It's mostly focused on information theory, but this group uses machine learning to do a lot of the things that we're trying to do with information theory. That'll become more clear as we go through the talk. Okay. So again, I just want to, with only a little bit of hyperbole, and certainly a little bit of hyperbole, I want to suggest that we're at a tipping point in the community. We've been using machine learning in hydrology for a long time. So the first example that I know of a machine learning model outperforming a process-based model at one of the central tasks in hydrology, in this case streamflow forecasting, was in 1995 by Kaolin, Hoshin, and Sarouche. Published this paper about using artificial neural networks for modeling the rainfall runoff process and compared their neural networks against calibrated Sacramento soil moisture accounting model. And the neural networks won across the board in all flow regimes in the areas they studied. So this was 1995. So I would characterize, when I entered the field in the mid 2000s, I would characterize the reception to this sort of result as lukewarm, right? This was the time when Chris Milley had published his 2008 paper, Stationarity is Dead. The conversation was about moving toward more physically based models and less conceptual models. And we now have things like the National Water Model in the United States, which is a continental scale distributed hydrology model. We're talking about hyper-resolution models. We're talking about representative elementary watersheds. And this is where the conversation was when I entered the field about 10 years ago. But it didn't. The fact remained that if you really just wanted the best stream flow predictions you could possibly get, if you were a reservoir operator or if you were doing flood forecasting on a daily basis, you really wanted to be using machine learning. So this has been true for 20 plus years. Recently in hydrometeorology, a group, a research collaboration led by the UK Met Office, this is Martin Best at the UK Met Office, took 13 of the world's most sophisticated hydrometeorology models that are run by many of the weather and climate forecasting centers around the world. These are operational models run in their operational setting. They're things like Cable from Australia, COLA from the United States, ISPA from France, JULES from the UK, Mosaic from NASA, NOAA from the National Oceanic Atmospheric Administration, so forth. And these are run in their operational settings. And Martin compared them, Martin and Gab Abramowitz at UNSW, compared these against piecewise linear regressions, spline regressions, and found that simple regressions can often outperform our most sophisticated hydrometeorology models at predicting half-hourly surface energy balance. So that's latent sensible heat fluxes given net radiation at the half-hourly timescale. And they did this at 20 different FluxNet sites around the world. So we extended that work and we compared these same models at the same sites with neural networks. And we found that if you train a neural network, so these are the sites down here that we looked at. These are the PALS, Gab's PALS sites, the protocol for analysis of land models. These are 20 FluxNet sites with sufficient data record that are clean data and few missing data, few gaps. So we're predicting latent heat, sensible heat, and net ecosystem exchange. For the purposes of this talk, we're using neural networks to predict latent and sensible heat. And we trained 2 types of neural networks. One, we trained a single neural network to predict at all sites. So we did leave one out. We took one site, left it out, trained on 19 other sites, and predicted at the one site we left out. And then we measured the amount of information using the mutual information metric that that leave one out model provides about the half-hourly time series of latent and sensible heat fluxes. And then we did it a different way. We did a split record. So that's this black bar. This black bar here measures the amount of information provided by a neural network trained out of sample, seeing no data from the site where it's making predictions. And this is the amount of information that we get from that model about the observed time series of latent heat flux. And this is averaged over all of the 20 different sites. So we did that leave one out strategy 20 times. Over here, this gray bar, this is the amount of information we get out of a neural network where we do a split record training. So we take the time series at each site, we divided it up into 5 chunks, we do 5-fold, k-fold validation, and then we measure the information in the out of sample predictions, but where the model is trained at a particular site and used to predict at the same site in a different time period. And of course, that model does better because it understands the dynamics of that particular site. And we get about half as much information from a single global model that doesn't have access to any information about the differences between sites. But what's interesting here is that the models, the operational models that are run in their operational setting at these 20 sites, they do generally worse and only ever just slightly better than a neural network that has no place-specific information. So what we're seeing here is that that the neural networks are doing naive, just absolutely naive neural networks are doing as well at one of these sort of fundamental tasks as our most sophisticated hydrometeorology models that have had quite literally tens of millions of dollars of investment and development over decades for each one. Okay, and I built this neural network in an afternoon. So the question is, how can we reconcile these things? Is there any value in these hydrometeorology models that can be added to the neural networks? Is there value in the neural networks that can be added to the hydrometeorology models? So I see this as the motivating question. Okay, so here's a list of the models that we tested, and here's a sort of a blow up on the results. And again, this is just a really, really simple application of a feed-forward neural network. The models are doing better than our neural networks at carbon flux prediction, by the way. Okay, but focusing on just the surface energy balance, the neural networks, these naive neural networks are doing really well, even the out of sample neural networks. Okay, we have similar results in hydrology. So this is back to streamflow forecasting. These are new results, and I'm not going to spend a lot of time on this because these are really Freddie's results that he's going to talk about next week. But I just want to mention that they exist because they motivate what we're going to do in just a minute. So these are the pink are Freddie's long short-term memory networks. So this is my attempt to recreate Freddie's work that he'll present next week. So these are numerically different than what he'll show, but basically this work should credit him. So these are long short-term memory models. This is a type of recurrent neural network that has a state variable. Actually, we use 125 memory states, and we took 670 catchments from the CAMELS database. The CAMELS database is 671 catchments, mostly natural catchments. It's released by NCAR. Each catchment has about 30 years of daily streamflow data and 30 years of forcing data. And also NCAR publishes a calibrated Sacramento soil moisture accounting model for each site. So in the NCAR's SAXMA model, which is in green here, they've taken the Sacramento soil moisture accounting model and they've calibrated it 10 times using shuffled complex evolution at each one of these 670 catchments. Okay. So they use 15 years of the full data record to calibrate, and they validate on the next 10 years. And we report the Nash-Sutcliffe efficiency of the log transform streamflow in their validation period. So the green model, the green Nash-Sutcliffe efficiencies, green histogram here, counts the Nash-Sutcliffe efficiencies from a range of -1 to 1 of a well-calibrated Sacramento soil moisture accounting model. This is a model, again, that's been calibrated separately for each basin and validated on a split time record validation procedure. The LSTM is different. Our LSTM here doesn't use any data from the catchment where it makes predictions. It's trained on we used k = 7, a 7-fold k-fold split, and we took 6/7 of the catchments, trained a long short-term memory network using the first 15 years of data from 6 out of every 7 catchments, and used it to predict at the catchments that were not used for training. And we repeated that procedure 7 times so that we got out of sample predictions for every basin. So the SAXMA here is a gauged model, calibrated daily, 15 years of data. I would suggest that this is probably the most accurate streamflow model that we have. Process-based streamflow model, I don't think you're going to beat a calibrated Sacramento soil moisture model. This is the long short-term memory network that's an ungauged model. It's predicting out of sample. And what we see is that the ungauged neural network beats the gauged conceptual model. Down here, we make the same comparison against the National Water Model run by the NOAA National Water Center down here in Tuscaloosa. And of course, the neural networks beat the National Water Model. So I just want to point out what's happening here. Neural networks are doing better in ungauged catchments than arguably our best hydrology models do in gauged catchments. And that's a big deal. We can't not pay attention to that. So we have really, I see two ways forward for the field. One is that we recognize that machine learning is doing better in some of our most fundamental hydrology tasks, and the people that care about making forecasts will start doing their forecasting with machine learning. I think that's probably what's going to happen. I think Google is going to release flood forecasting everywhere soon enough, and I think that the people that fund us to do streamflow forecasting, us meaning people in the hydrological sciences, will probably stop doing that, and I would hope that they would, because I think that in the 75 years that of hydrologic science, we've kind of failed at our main tasks. We've failed at deriving scalable hydrologic laws. I think the 1986 Duke paper, looking for hydrological laws, where he says that we don't have scalable hydrology laws that work across watersheds, I think that still holds true. I think that those scale relevant laws probably exist. I think that what we're seeing in these machine learning results is that there are patterns in our data that if we had been better at our jobs, we could have extracted those patterns into scientific insights, but largely we haven't done that, and we haven't done that in a way that we can encode in predictive models. The machine learning models are telling us one thing very clearly. They're telling us there's more information in our data than we've been able to extract by building process-based models. Okay, so the question is, what's the path forward for the hydrological sciences? There's two, I see two paths forward. One is that we just don't do hydrology in the traditional sense anymore, or at least that part of hydrology plays a continually decreasing role in informing the models that we use for operational predictions. The second strategy is that we make a concerted effort to understand where there's information in our process-based understanding of hydrological catchments, and we use that. We figure out how to integrate that into these new emerging techniques to draw information directly from data. So that's the purpose of this talk. Where is there information from our process-based understanding, and more importantly, how can we merge that with these new technologies that are really efficient and really good at extracting information directly from data? Okay, and I again, with only just a little hyperbole, but certainly a little hyperbole, I would say that this is an existential question for the hydrological sciences. If we don't answer this, our role in the world will be very different than it was in the last decade. Okay, so let's go back to the Milley paper. The hypothesis in the Milley paper is that stationarity is dead. We can't rely on data-based models to make predictions going forward into the future because of largely anthropogenic non-stationarities. So humans are changing hydrological catchments either through land use, land cover changes, anthropogenic water demands and withdrawals, or even just through climate change, right? So if we want to understand, if we want to plan, engineer for the future, we have to use process-based models, because the idea is that a process-based model understands the relationship between the boundary conditions, things like temperature and precipitation, and the responses that we care about, things like flooding depth, stream flow, ecological productivity, drought, surface energy balance, et cetera, et cetera. Okay, and the idea is that machine learning models or data-driven models are only good insofar as they have available training data. So they're not reliable outside of situations that are similar to the available training data. Okay, so let's test that. Let's test that theory. So this is an example of testing that theory. We're worried about predicting net ecosystem exchange. So we want to map carbon flux globally. Okay, We have about 70 FluxNet towers there are 340 FluxNet towers globally that have some data record, and about 70 of those FluxNet towers have sufficient data to train and test neural networks for daily flux estimation. Here we're going to look at estimating sensible heat, latent heat, net ecosystem exchange, and soil moisture. Okay, so we're going to build a neural network at each one of these sites to predict these 4 variables from inputs like air temperature, net radiation, evaporation, air temperature, net radiation, precipitation, wind speed, and the usual meteorological variables from FluxNet. Except we're going to divide our time period up based on a known non-stationarity. Here we're going to use the ENSO index. So we're going to divide our model building exercise up into periods where the ONI index is above 0.5. We're going to call that El Nino periods, where the ONI index is below negative 0.5, which we're going to call La Nina periods, and where the ONI index is between negative 0.5 and 0.5, and we're going to call that neutral periods. So we're going to build 3 sets of models at each one of these different sites. One set of models is going to use all El Nino period data and all La Nina period data to predict neutral period data. Another set of models is going to use all El Nino period data and neutral period data to predict La Nina period data, and so on and so forth. And we're going to see if we can predict out of sample, right? So we have this idea that the ENSO cycle will change the ecosystem behavior at least a number of these sites. We're going to first identify that sites that have differences in ecosystem behavior between El Nino versus La Nina period, and then we're going to test whether machine learning models built at those sites can capture the ecosystem behavior in the out of sample period. So we're going to test this non-stationarity hypothesis. And the way we're going to quantify ecosystem behavior is through information transfer networks. So this is some work that came out of Praveen's lab with Ben Ruddle in 2009. These are information transfer entropy dynamic process networks. And basically what we do is we measure the information flow, the relationship between one of the input variables, say temperature, with one of the target variables, say soil moisture. So at some time scale, temperature has some influence on soil moisture. Okay, so we're going to formalize this concept in just a bit, but for right now, just think of it as a metric that measures the nonlinear correlation or nonlinear relationship from one variable to another, between 2 variables. And we expect that the relationship between temperature and soil moisture will change depending on ecosystem functioning, and that ecosystem functioning will be at least somewhat probabilistically dependent on an externality. And our externality that we hypothesize here is the ENSO index, ONI index. Okay, so let's test the hypothesis first. The first hypothesis is that the ONI index predicts differences in the information transfers between variables in at least some of our ecosystems, and so that we're testing that hypothesis on these 2 plots here on the left, right? So the top plot shows information transfers from one of the variables, say air temperature up here on the y-axis, to one of the receiving variables, say latent heat flux. So air temperature is sending information to latent heat flux, and that's quantified by this top left square here. And what the color of this top left square represents is the fraction of sites where there's a statistically significant difference between that information transfer during neutral versus La Nina periods. So we've taken all of the sites with enough data, we've randomly sampled them to create a background distribution of differences between information transfers, and then we've sampled the site, every particular site based on El Nino versus La Nina period, and calculated the differences in information transfer based on that split, that indexed split. And we see that some of these information transfers do depend very heavily on the ONI index at least some of the sites. So the yellow color means that 60% of those 70 sites have a statistically significant difference in that particular type ecosystem function between neutral and La Nina periods. Okay, and so this is the difference between neutral and El Nino periods, and this is the difference between La Nina and El Nino periods. And so what we really see here is that the surface energy partitioning is different in something like half of the sites between neutral and El Nino periods. So what this graph is telling us is that we have a natural laboratory that can, at least to some extent, test the hypotheses that machine learning is not predicting well out of sample. Okay, so what we do is we train a machine learning model, as I described earlier. We train a neural network that takes data from 2 of our types of time periods and uses it to predict data at the 3rd type of time period. And then what we want to do is we want to test, and we do that with all 3 time periods, so we get out of sample predictions for every site. And then we want to test whether the difference in ecosystem functioning between the 2 sites is captured by the difference in the predictions made by the machine learning models. And the answer is certainly no. So that's on the bottom right-hand side here. We're looking at correlations between the modeled versus observed differences between ecosystem transfers, between information transfers between different ecosystem components. And we see that in all except a very few cases, there's very little correlation. So it is the case that there is a danger in using machine learning models to predict out of sample. Okay, so there's two things that I want to draw attention to here. One is that we're doing this for latent sensible heat, surface water content, and net ecosystem exchange, and that there is a difference between these 4 variables. We saw earlier that the naive single layer feed-forward neural networks were able to predict latent and sensible heat flux at the half-hourly timescale, but they weren't very good at predicting net ecosystem exchange. And we kind of see just a little bit of indication of that here. The latent heat flux as the receiving variable. The machine learning models are able to tell something about the surface radiation partitioning into latent heat flux, even when trained out of sample. But other than that, these things are not super reliable out of sample. Now, here's the question. Is there a dynamical systems model, let's say a NOAA-MP land surface model, for example, that is able to capture these things? And the answer to that is that we're looking. So I'm not presenting results here because I'm not very happy with our results. But if you calibrate NOAA-MP at each one of these sites during these different periods, you will see. We expect that you will see similar results. Okay, so what we have here is kind of a problem. We have a problem in that the tools that we have that make the best predictions do have these sort of known deficiencies, right? We would like to use physics to constrain, or biogeophysics to constrain predictions by machine learning models in cases where those machine learning models might be expected to not do as well as we would like them to do, right? So how can we merge the physics of our process-based models with this sort of unprecedented and in my subjective experience, sort of just amazing ability of modern machine learning methods to extract information from data. The first thing that we can do is start to say where the process-based models go wrong. Okay, so now we're going to look at NOAA-MP in detail. NOAA-MP is a land surface model that attempts to predict these 4 variables here that we talked about earlier: latent heat flux, sensible heat flux, surface soil moisture content, and net ecosystem exchange. So we'd like to know where in that model things are going wrong. And we know things are going wrong because NOAA-MP is a close cousin to 3 of the models that we tested in the hydrometeorology example that we motivated this talk with at the beginning. Okay, so the NOAA family of models is not doing as well as neural networks at predicting half-hourly sensible and latent heat fluxes. And so we'd like to know where in the model things are going wrong. So here's the strategy that we've developed to do that. This is what we're calling process diagnostics. And this is our basic strategy. We have an information transfer diagram like this. Every color on this diagram represents a different variable that's simulated by the model and also that's observed by some observation network. So here we're going to compare NOAA-MP with FluxNet tower data. So we have things like leaf area index, net ecosystem exchange, sensible heat here, latent heat flux here, net radiation, top layer soil moisture, second layer soil moisture, air temperature, and here's the model resistance, which is only modeled. We don't measure that, but NOAA-MP does models to model resistance as a latent variable between soil moisture and, for example, evapotranspiration. So we quantify the information flow between two variables. So let's say that soil moisture has some influence on latent heat flux, right? So soil moisture controls evaporation to some extent at some time scale. If we know the soil moisture now, that tells us something about what the evaporation will be at some time period in the future. If we know the soil moisture today, that tells us something about what latent heat flux will be either today or tomorrow. If we know the soil moisture right now, this instant, let's say averaged over a half hour, we can tell you something about what latent heat flux will be either this half hour or the next half hour. And that predictability, that measure of predictability, is an information transfer between these two variables. It's just a measure of the strength of connection between two variables across some spatiotemporal scale. And we quantify that using information theory. Information theory in this equation up here, it says the mutual information between the variable that we want to predict at some S time period in the future. T is now, S is some number of time steps in the future. The variable we want to predict at some time steps in the future shares some information with the variable is our sending variable that's sending information right now, and we're going to condition that on the value of the predicted variable now. This is called a transfer entropy network, and basically what it's doing is it's asking it's integrating something like the ratio of the probability of the variable that we want to predict, conditional on the variable that we're going to use to make the prediction, so the receiving variable conditioned on the sending variable, over the probability of the receiving variable that's independent of the sending variable. So it's asking us, how does the probability distribution change if we condition the variable that we want to predict on the variable that's sending information versus if we don't make that condition? So the larger this integrated number is, the larger this difference is integrated over the whole probability of all of the variables in the three-dimensional probability density function, means that there's a stronger relationship between the two variables. And it is directed, and it's directed because there's a time lag here. It's also directed because we're conditioning on the Markov state of the receiving variable. Okay, so this tells us how two variables are related in a dynamical system. And we can also measure the accuracy of the model at predicting any variable that we want. So we can measure, for example, the information transfer from soil moisture to latent heat flux, and we can also measure the accuracy of the model at predicting latent heat flux. These are two different types of things that we want the model to do. We don't just want the model to predict accurate simulations of all the variables. We also want the model to predict accurate couplings between each of the variables across spatiotemporal scales. So we're going to separate these two objectives into two types of objective functions. We're going to call one predictive performance. That's just the accuracy of the model. That's on the y-axis of this chart over here. That's the accuracy of the model at predicting any of the variables that we care about. For example, we're going to choose latent heat flux. So the y-axis plots our objective function measure where 0 is better, 0 error is better, 1 is the worst possible model, according to whatever performance metric we're going to use. And this is just the ability of the model to recreate the time series of latent heat flux. This could be a mean squared error. It could be an inverse mutual information metric. It can be anything we want to use to quantify the performance of our model. The functional performance is this information transfer. And what we want is the information transfer in the simulated system to be equal to the information transfer in the observed system. So this is a difference between the transfer entropies modeled versus measured transfer entropies. And ideally, we want the difference between the modeled versus measured transfer entropy difference to be at the same point so we're going to vary the model parameters. So we have three models here. We have model A, B, and C. These are three different models predicting the relationship between soil moisture and evapotranspiration. And ideally, each curve is derived by varying the parameters of the model. So as we vary the parameters of model A, we see that model A makes its best predictions about latent heat flux at the same point where it makes its best predictions about the relationship between soil moisture and latent heat flux. So model A is our ideal model. We can find a parameter set that gives us the right answers. That's the predictive performance for the right reasons, which is the functional performance. Models B and C don't behave like that. Model C, we can get really, really good predictions of latent heat flux according to against whatever observation data we have available, but it's not at the same point where soil moisture exerts the correct control over latent heat flux. So model B and C have clear indication of model structural error. Not only that, but clear indication of model structural error in this particular relationship. So this is just looking at one particular relationship from soil moisture to latent heat flux. And so what we're claiming is that Pareto trade-offs are an indication of process-specific model deficiencies. So we can see what that looks like in time. This is a video, we're going to play in a minute, but what we have is one FluxNet site. This is the Amplero grassland, I believe, in Italy. We're going to change the time scale. So we're going to look at information transfers between all of these variables, which are temperature, wind, carbon, humidity, precipitation, soil moisture, evaporation, sensible heat flux, and radiation. We're going to look at the couplings between each of these variables over different time scales. So the time scales down here are going to change, and this network of information transfers is going to change. And if you stare at it long enough, which we won't do here, but if you watch this video over and over again, you'll see patterns in how these information transfers change that make sense according to what we know about the system. Then we're going to do the same thing for the model. And here the model is the NOAA-MP land surface model, and it's simulating relationships between all these variables. And so the simulated information transfers will change in the model with time scale as well. We're going to subtract the two. We want the difference between these two graphs to be 0. And we're going to plot the overestimation, the places where the model overestimates couplings between two variables. And we're going to plot the underestimation, so the places where the model underestimates coupling between two variables. And we're going to do that across time scales. So we can let this play. And what we see in NOAA-MP, this is just an example of the concept, but what we see in NOAA-MP at this particular site is that carbon flux, which is the dynamic it's coming from the dynamic vegetation of NOAA-MP, is largely decoupled from both the water components, which are in blue, soil moisture, humidity, and precipitation, and the energy components in warm colors, wind, temperature, and radiation. So the major underestimations of relationships in the NOAA-MP relative to what we see in observation data is NOAA-MP is not correctly simulating the role of the water and energy cycle on growing photosynthesis. And we can see that across time scales. So if you were to go into NOAA-MP and you would say, I want to improve NOAA-MP, the key relationships that are not being simulated correctly in NOAA-MP are related to dynamic vegetation. So this is what these Pareto trade-offs look like in a model. This is a model that Darren Drury built out at JPL with Ben Ruddle and Praveen Kumar. And we can see that what we're doing here is we're looking at different sending variables. LAI is sending information to latent heat flux. Precipitation is sending information to latent heat flux. Net radiation is sending information to latent heat flux. Here's sensible heat flux, and here's the carbon emissions. This is carbon production by the ecosystem. And we see these sort of Pareto fronts very clearly when we vary different parameters. So here we're varying the M-slope parameter, which is this model related to stomatal resistance. For our purposes, it doesn't really matter what's going on, but this is just an illustration to show that as we vary the parameters in the model, we do get these Pareto fronts, and we get different Pareto fronts for different relationships. So here's precipitation in orange sending information to sensible heat flux, versus this yellow line here, this yellow Pareto front here is net radiation sending information to sensible heat flux. So the plot on the right is interesting because the top plot is the MLCAN. This is the dynamic process network, sending information again between the different variables listed here: LAI, precipitation, net radiation, temperature, wind speed, vapor pressure deficit, and solar zenith angle to carbon production, FCO2. And we see that there's clear indication by varying the M-slope parameter, there's clear indication of error in the model in each of these processes. They're minimizing their predictive error at places that don't minimize their process error. So they're getting the right answers for the wrong reasons. This is a way to measure getting right answers for the wrong reasons. Compare that with an artificial neural network. So we trained an artificial neural network and tested it using this method out of sample. And we see that in this particular case, the artificial neural network has Pareto fronts that are at least closer to the ideal, which is the zero minimum point right here on the axis. So this is another sort of clear case that, well, it's not a clear case because we're not calibrating MLCAN as well as we could, but it shows you how you can compare the functional versus predictive accuracy of process-based models versus machine learning. Okay, so go back to our original motivating example where we took the model from the models that were collected by the UK Met Office for the Plummer study. That was where Martin Best evaluated the 13 operational land surface models against 20 data from 20 FluxNet towers. And so these are us plotting those each of those models at each of those sites in this functional versus predictive accuracy space. Okay, so the plots on the right here are identical to the plots on the left. There's no difference in the data plotted between these two groups. Each subplot represents a particular information transfer pathway. So from air temperature to latent heat flux at the top here, air temperature to sensible heat flux again at the top, net radiation to latent heat flux, net radiation to sensible heat flux, net ecosystem exchange to latent heat flux and sensible, and then soil moisture to latent and sensible heat flux. Oh, apologies. Okay, so the same data is plotted on both sets of plots, but in one set of plots here, we've color-coded the data by model. So each model is a different color. And on the other, we've color-coded each piece of data by site. So each model, 13 models, run at 20 different sites. Here we've color-coded by model, here we've color-coded by site. And what we should see just by looking at this is that there's no pattern in the functional versus predictive accuracy for any model. So all these red models here are scattered throughout the cloud of where the models land in the functional accuracy space down here in the x-axis and the predictive accuracy space on the y-axis. So any given model is not performing in any particular way across all different sites relative to any particular process that's happening in the model, a process being like net radiation sending information to latent heat flux. If you color code by sites, all of the models are grouped. So we see clear grouping at these orange sites, which is the Sylvania site. I forget where that is, but that's one of our sites. The yellow, there's clear grouping in the models on this yellow site, which is called Palang. So you see clear grouping of behaviors of the models at each site. And what that means is that all of these models have similar error patterns. No model has the same error pattern no matter where you apply it, but all the models applied at one particular place have at least similar error patterns. And we can quantify that. So we can quantify the fraction of variance in the spread of each of these clouds due to grouping by site versus grouping by model. And grouping by model explains less than 10% of the variation, but grouping by site explains something like 40% of the variation. So the takeaway here is that from the current generation of land surface models, hydrometeorology models used by operational centers in the world right now, there are no clear error patterns that we could point to and say, this is the particular problem with that model everywhere in the world. The problem is that the models are not representing the site-by-site diversity very well. And also, all of the models are behaving similarly. So they're all wrong for the same reasons. So one thing we would not want to do here, it would not be beneficial. It would actually be misleading to take all of these models and run them as an ensemble and have that represent epistemic uncertainty. That would be an incorrect thing to do because they're all wrong for the same reasons or similar reasons. Okay, so how do we take that knowledge and how do we apply it to, how do we use information that we can extract from data to correct those problems? The old-fashioned answer is data assimilation. So we can assimilate data. We can assimilate observation data into our model to adjust the state vector through some pseudo-Bayesian, either formally Bayesian or pseudo-Bayesian method. So all data assimilation is effectively a Bayesian method in one approximation or another. And we can do data assimilation. So I'm going to assume that everybody knows what data assimilation is. This is an example of a discrete time data assimilation system like an ensemble Kalman filter. But what happens is that data assimilation can update the initial state, but it doesn't tell us anything about the systematic deficiencies of our model. It doesn't tell us anything about what's systematically going wrong in the model equations. So if TK is time now over here on this Lorenz attractor plot on the left, we can assimilate all past data and we can get a good initial state, and that does reduce uncertainty for a little time in the future. But eventually we're going to go back to being as uncertain as we would be due to the errors in our model. So data assimilation is great. Incidentally, we wrote a paper a couple years ago where we measured the ability of the ensemble Kalman filter to extract information from soil moisture data. And we saw that the ensemble Kalman filter, because of the strong parametric assumptions it makes on the forms of the uncertainty in both the model and the observations, at least in one rather notable application of the ensemble Kalman filter to soil moisture data assimilation, it was only extracting 3% of the available information from the observation data. So we have a couple problems with data assimilation. One is it's really hard to implement. It's Bayes' theorem. Bayes' theorem is really hard to implement in a generative way because it requires estimating probability distributions, and estimating probability distributions is hard. So data assimilation is often inefficient. In principle, Bayes' theorem is nice. In practice, it's really often really hard to implement in a generative way. The other reason data assimilation is difficult, is not ideal for this situation, is because it doesn't store the information in the model structure, and it doesn't allow us to extrapolate what we've learned from past data into future predictions. Okay, so we're going to try to solve that problem. The way we're going to, the general, and here's my overall message. So this is the slide that matters in this talk. The goal is to use sophisticated ways to extract information from data, and by sophisticated, I am specifically mean not data assimilation. So we need sophisticated ways to extract information from data, and effectively we call that machine learning. But we also want to keep our physics that's in the models. And I'm proposing, this is completely my own sort of view on the world, but I'm proposing that there are three categories of strategies that we might pursue to do this. One is to learn physics from machine learning. One is to impose physics onto machine learning, and one is to combine physics with machine learning. And I'm going to describe exactly what I mean by that in just a minute. But just to give you a sort of a sense of the flavor here, my own review of the literature, I see that there's really a couple strategies for learning physics from machine learning. And by physics, I mean partial differential equations. So I mean formal descriptions of dynamical systems that are posed in a language that we would recognize as people that have grown up in a system that relies heavily on Isaac Newton's perspective for understanding the world around us. So there's a long history dating back 50 years or more of trying to derive partial differential equations from machine learning models. And as far as I know, and I look frequently, there's been really nothing that looks like success at this. This would be the holy grail. If we could derive PDEs from machine learning models, there would be no questions left about how to merge physics with machine learning. I don't see that as a likely option. Certainly, this would be the revolutionary discovery if someone made it. We could change the way we think about physics, and I think this is what's actually happening in our community and the larger science community. We're broadening our perspective on what it means to understand a dynamical system. So we could always do sensitivity analysis on machine learning, but purely anecdotally, I would say that most physical scientists don't see that as something like real understanding. I think that the machine learning community and its sort of impact on the world is starting to change how we see what we're willing to call understanding. So I think that if we're starting to see patterns that we can't necessarily express in equations that we can write on a blackboard in front of our students, I think that I see a growing tendency, purely anecdotally, in the community to accept that as something like real understanding. And I think that there's some really interesting philosophy of science out there now about I think we're looking at a major shift in what we think and what we call science, but that's a different topic. We can impose physics on machine learning models. So let's say that we're in a situation where the machine learning model is doing really, really well. And we just want to make sure that it obeys some physical constraints whenever it gets outside of the training data or even inside of the training data. There's some really easy ways to do this. We can regularize the loss function, so we can impose penalties in the training of the machine learning for violating physical constraints. We can do semi-supervised learning so that one network throws away predictions that violate physical constraints made by another network, and we can embed that in a training procedure. So that'll be like an adversarial network. And we can impose hierarchical constraints in model architecture. So one open question, I think, in the streamflow modeling is, when we move from lumped catchment modeling to distributed modeling, can we give the network a digital elevation map as a input, and can it learn that water moves downhill? Or are we better off imposing a drainage matrix, a connectivity matrix, and forcing it to only let water move downhill? So I think that would be a great experiment. But in general, I think that the open question is where and when we put hierarchical constraints in model structures. So whereas I said before that driving PDEs from machine learning models would be a holy grail, and I doubt that we'll ever do that, imposing hierarchical constraints on model architectures is sort of the heuristic or ad hoc thing that I think that our community should spend a significant amount of time focusing on. I think that if we can learn as a hydrology community, as applied science community, where our past knowledge and understanding of these systems benefits these emerging machine learning architectures and figure out ways to impose that information into the structure of the models, I think that that's where we'll anchor value in the physical sciences, which I certainly hope doesn't go away. More generally, I think there are general solutions for the problem from combining physics with machine learning, and in particular, I would advocate. I think about this in terms of graphical networks. So you can decompose a process-based model into a graphical network like this. This is the SUMA land surface model from NCAR, and each one of these orange and blue circles here, nodes in the network, is a different variable that the model is simulating, and each black arrow is a relationship. So information flows along each of the black arrows here. There's some connectivity between each of these variables in this graphical network. And ideally, what would happen is that we would have a graphical network that looks like this, that lets us impose our conceptualization of the system onto our model. So we conceptualize that there's something called soil moisture, and we conceptualize there's something called surface runoff. So we conceptualize these physical variables, and by physical variables, what I think that I mean are variables that obey symmetries. So typically what we mean by a physical variable is a variable that obeys some sort of conservation law or some sort of symmetry principle, which of course are the same thing. And so having the ability to impose my conceptualization or my perception of the system into a graphical network, a reductionist network like this, and then for each edge, we need to assign either an equation, either a process-based equation, or ideally we would have the ability to assign a separate machine learning model for each edge or each group of edges in the network. And then we should be able to replace these edges with hypotheses, with process-based hypotheses, and see whether those hypotheses, whether replacing a machine learning edge with a structure hypothesis adds information or subtracts information, given the situation will always be that the training of a huge set of networks like this will be underdetermined relative to the information and the data that we have. Okay, so I see that as a set of long-term goals that we might aim for if we want to understand the role of traditional process-based science in the new world, the new age of machine learning. And again, I think that's a serious existential question for our community. The way that I've been attacking this personally is a much simpler strategy. Here we have a PDE, dxdt, the evolution of some state variable. We have a process-based model, which is the F model here. So this dxdt equals f of x is our traditional PDE system that we're going to solve. So this would be, this SUMA model is posed as a PDE like this one. And what we can do is we can add a machine learning kernel to it. So when we do data assimilation, we take a dxdt equation like this and we add some random walks. So instead of this GP mu, we would add some eta, and it would become a stochastic PDE. And one of the very simplest things we can do, instead of adding stochasticity to our partial differential equations, we can add structure. So we can just add a machine learning kernel as another flux term in a dxdt relationship, and then we can use the data to learn this flux term. So we're really learning something like the deviation of the model from observations at a time step level. So how does the model predict evolution of a state variable at a time step level differ from how we observe the evolution in the system? So this is a very, very simple thing to do in principle. In practice, it's actually quite difficult, but in principle, it's a very simple thing to understand. And then if we have a stochastic machine learning model, so GP here stands for Gaussian processes. And I like Gaussian processes because for a few reasons, they revert to zero mean when they go outside of the training data. So when there's no observation, when we're in a situation that's dissimilar to observation data, the model reverts to the dxdt equals f of x with no input from the machine learning. So GPs do that naturally. Also, GPs have an uncertainty term, so we still get a stochastic PDE, but we learn something about the time evolution of the stochastic part. Again, it's just Gaussian at every time step, but at least that distribution changes depending on the state of the system, the input variables, and the parameters of the system. So this is one very, very simple and certainly not the end story about how to do this, but at least we have a structure now that lets us both simulate with known biogeophysics, but also lets us impose structures from data onto the time evolution of our dynamical systems. So we've done this with the high-mod rainfall runoff model. We took high-mod, which has a nonlinear soil moisture tank, and it has some routing functions that turn into stream flow, some quick flow routing tank, and some slow flow routing tanks turn into stream flow. We turn that into a Bayes network, a graphical network. We learn a different Gaussian process for each of the edges in the network, each of the relationships in the network. Then we train a Gaussian process based to emulate the original model. So we calibrate the model with available data. We estimate the model parameters. Then we train the actual high-mod parameters. Then we train a Gaussian process to emulate the model. Then we perform some nonlinear smoothing, preferably some non-parametric smoothing, something that looks like data assimilation. And then we retrain the Gaussian process emulator on the reanalysis state. So we're retraining the Gaussian process emulator to give us something that would look like what data assimilation would give us. When I say data assimilation, we can use something as simple as a Kalman filter and just live with the fact that it's not getting full information extraction from data, or we can use something more sophisticated like a Dirichlet kernel, and that idea was published by Natalia Boligina, Natalia Levine, and Hoshin Gupta in 2010, 2011. So this can be as sophisticated or as unsophisticated as you want, but what happens is whatever information you're extracting from data assimilation, you're encoding it into a new model, and you're encoding it into a model that takes this form. It's the original model plus some correction that's learned, that has the ability to learn patterns from data plus some random noise term. Okay, and we can do that with high-mod, and we can look at what happens. So if you look at this plot of results here on the right, we take the model alone. We have a 3-year observation period and a 3-year forecast period with no data. If we take the uncalibrated model, we have some mean squared error. If we do parameter estimation on the model, using data from the 3-year assimilation or 3-year observation period, the mean squared error goes down in the assimilation period, in the calibration period, but also it goes down in the forecast period because we have better model parameters. We can perform traditional data assimilation on the high-mod model, and that reduces the error in the model predictions by a lot during the observation period, but it doesn't during the forecast period because none of the information from data assimilation is stored in the model. Then we can perform this system identification by adding this Gaussian process term in place of the random walk that we had to add to do data assimilation. And we see that that's storing some of the information that's gained from data assimilation. It's storing it into the predictive model structure and allows us to make more accurate predictions going forward into the future. So we have some ability. So this is just a toy demonstration that we have some ability to learn from the error patterns of our models directly from data by combining machine learning with traditional differential-based models. And then we can apply our process network analysis to this to see where that procedure changed information flows in the model. So we develop a process network for the high-mod model alone, and then for the high-mod model as it ended up after we did this expectation maximization procedure to encode the information we got from data assimilation into the model structure. And we can see that the model structure changed. So we can see that the information transfers between variables changed. And in sorry, there's no color code on here, but the red means that it changed a lot. Blue means it didn't change very much. Green means it changed a little bit. Red means it changed a lot. And where we're really seeing the model changed, and again, we're assimilating streamflow data, so it's only seeing precipitation, potential evaporation, and streamflow data. And where this procedure said that the model needed to change was in the relationship between soil moisture and precipitation, which is the infiltration function. It's the part of the model that this procedure indicated was contributing the most error, and it changed it the most, and that resulted in better out-of-sample predictions. So we can look at these response surfaces, and we can see that on the right here are the response surfaces of the original high-mod model. That's how two variables interact to predict the third variable in the total model state. And we can see that most of the relationships in the original high-mod model are linear, but after we do the expectation maximization procedure, these response surfaces curve and we introduce non-linearities into the model. And so we can kind of see that this procedure has changed the model and it's added complexity to the model. Okay, so I'm almost out of time, and I just want to leave this slide up because I think this is my main message. I think that what I would really love to see happen in the community is a concerted effort to understand where our where our understanding of hydrological catchments and hydrological systems adds value over what we're able to extract from data now that we have these ever-growing, these really large Earth observation data sets and these really powerful methods, non-heuristic methods for extracting information from data. All right, thank you very much.
Thank you very much, Gray. So the official time, I think, is up until 2 p.m., but as a webinar, we have as much time as we want. So I'd like to, for those who are still interested, I'd like to take about 10 minutes or so to ask some questions that were raised during your talk. For example, one of these questions, one second, I lost the name of that question, asked by Giuseppe Amatudi, is how can we take into account temporal dimensions inside the machine learning model? I think we have some answers to that, but I'll let you take this one, Ray. How do we take account temporal dimensions? For example, snow cover in the winter would melt in the summer. How can we take into account upstream conditions to downstream conditions?
Yeah, I think it's a great question. I'm going to punt a little bit because I know that Freddie is going to talk about that exactly next week, even down to the example you gave. And I don't want to spoil Freddie's work because it's actually some of the most amazing work I've ever seen, to be perfectly honest. But let me just say that these recurrent neural networks, they have a state variable in them, and I don't want to steal Freddie's talk, but what I think Freddie will show is that they're actually learning hydrologically relevant variables, like snowfall. So the LSTMs are cool because they have a state variable in them, and they have a natural time evolution of just like we imagine any dynamical system.
All right, thank you. Yes, so let's keep Freddie's talk next week fresh. Thank you. Now, next question is, in what sense could a random forest model already include the knowledge of information gained when they construct the model? By Joanna.
Yeah, so is the question about how you can, how the random forest can represent what you already know about the system, or how the random forest you can measure because I know the random forest you can measure it has a natural sensitivity analysis, so it can measure the information content of any individual inputs. Is that the question, or is the question whether it's possible to impose hierarchical structure on the decision points in the random forest?
I guess you can't go back and forth here. The second one, should I say?
The second one, yeah. So I'll be honest, I don't know. I think that's great. If you were to find, look, I'm just gonna ramble because I don't really know the answer to that question. But my experience with random forests is that they're really powerful, and they're really powerful for smaller data sets. As an example, Nanzador at INCAR published a paper recently where he was trying to use machine learning to predict hydrological signatures from catchment characteristics. And he had a sample of 670, which in the machine learning world is a really small sample. And he ran random forests, I ran neural networks, and his random forest did better. And I think that what's happening there is that when the data set is small, that a more hierarchical structure like a random forest then is often better able to navigate that data structure. And so there are tipping points in the random forest. There are choice points in the random forest. And I think it's probably reasonable to, a reasonable project to go in and see if you can impose your a priori understanding on some of those tipping points. But that's all I would have to say. I think it would fit exactly in this second box here, impose physics as hierarchical constraints on model architecture.
Okay, great. So there are also some, let's say, educational questions. For example, it was asked, how do we get started with machine learning? And also, how is some useful papers. So I'm not going to almost just promoting myself, but we do have a review paper on this topic where you can get started on reading, and I posted that link in the chat box. But if Gray have some other suggestions, please go ahead.
Yeah, I think about this a lot because I teach machine learning here in hydrology to geology students here at Alabama. I actually teach geostatistics, but nowadays geostatistics is not you can't call it a geostatistics unless you at least teach machine learning. And so so here's been my experience in terms of ramping up with machine learning. When I started this project about 10 years ago, all of the code that I was using and I was borrowing from other people was largely written in MATLAB. And usually I would have to take their code and modify it, spend several weeks, several months modifying it to do what I wanted it to do. That is not the case anymore. So nowadays, you have really, really powerful machine learning tools in a MATLAB graphical user interface, and you can get some idea of what's happening with your data set just by pushing buttons, and you really have to do very little coding to really get a sense of what's happening. Now, if you want to do a publishable project, you will have to write some code, but if you've never used machine learning before, one very easy thing you can do is just use the regression learner or the deep learning learner in MATLAB, and that's a really great, personally, I think that's a really great introduction to the topic because it's hands-on. It doesn't require that you, it doesn't require really that you learn any new coding skills. There's just a tiny bit of coding required to import your data into MATLAB. And the click buttons it has are really good in terms of letting you choose between the types of things that people often like to do, like k-fold validation or changing the number of neurons or trying different kernels in your Gaussian process. So when I encourage my students to learn this, we start by using the MATLAB regression learner as the first place. Now, one more thing to say to that, the world doesn't use MATLAB anymore. Now, if you go and you get machine learning software from any of the computer science groups that are developing theory, again, 10 years ago, most of that was coming out in MATLAB, but now it's all, of course, coming out in Python. And my experience using the Python toolboxes like Keras is that they're just dead simple. They're just absolutely, completely, I don't want to say trivial to use, but you can get up and running with them in a day if you have background coding skills. So the situation is really different than it was 10 years ago. 10 years ago, in order to use these things and to explore ideas related to machine learning, you had to actually do some coding on the internal of the models. Even the best neural network toolboxes, you had to actually go in and modify the code. Nowadays, if you want to just start to play with your problem set in the machine learning space, honestly, you could be up and running in an afternoon using Keras or MATLAB.
Cool. How about, I have a question for you. When you derived your, a more technical question, when you derived your model physics metric, what was that? Sorry for the name misnomer, but you have a performance metric and you have another metric, which is like how model performs. When we go back to a few slides, yes, this one, a functional performance. So essentially this is a measure of information flow between different variables, right? The way I understand it.
Yeah.
But with the information theory, I feel like there's a big danger that is, we cannot distinguish between causal and associative relationships. That means you could just be lucky or unlucky to get some spurious relationships. So if you use these relationships to kind of benchmark a process-based model, you might be going in the wrong direction. So
So there's always possible. So anytime what we're really talking about here is theory of hypothesis testing, and there's any theory of hypothesis testing, there's always the potential for spurious correlation. So the old frequentist strategy, you see that explicitly in the alpha level. So 95% probably, p-values, the relationship between p-values and alpha value is exactly the same problem. So there's some probability that the data you have that you're testing your model against gives you that result as just by random chance. And by random chance in this case, what we mean is that your time series or your sample set that you're using somehow has less degrees of freedom in it than the model you're trying to impose. So there's some spurious correlation between the finite data sets that you have. Of course, you have infinite data sets. There's no such thing as spurious correlation. It only happens because you have to test against finite data sets. I'll just say this. There is, that is a fundamental problem. It's true for any evaluation metric, any hypothesis testing metric, any probability metric that you use, that there's always some chance that the patterns that you've observed. So science is the process of testing hypotheses against data. In order to do that, you know, in a traditional understanding of the scientific method, your hypotheses have to be translated into a model, because a model is the tool that makes predictions. And then the way you test the hypothesis is you compare the predictions with the observation data. So if in that case, whenever you compare predictions with observation data, there's always a chance of spurious correlation. So the question here is whether in information theory, whether you can put, there's two questions, whether you can put bounds on these, whether you can put probability bounds on these metrics like you can on something like a p-value. I mean, a p-value is a probability bound. So can we get distributions over the information transfer networks? That's the first question. And the second question, the second thing that I didn't go into here very much, is that these are actually bounded in one way. So information theory, because of I won't do justice to this, but we have a couple papers on it if anybody's interested. Information theory has a very interesting theorem in it called the data processing inequality. And what the data processing inequality says is that if you...
Looks like you dropped.
Yep. Can you hear me?
Now you're back.
Oh, okay. So there's a very interesting theorem in information theory called the data processing inequality. And what it says is that when you estimate information content, your estimate is always bounded above. So your estimate is always a low estimate of the true information content. And that's not true in any probabilistic sort of hypothesis test. In probability theory, if I do a probabilistic hypothesis test, either a Bayesian test or a classical frequentist statistical test, I have the p-value could be overestimated or underestimated, right? I always have some probability of type 1 error or type 2 error. In information theory, that's not the case. The data processing inequality says you're always going to underestimate information. And if you decompose that in a smart way...
Oops, great drops again. Let's see if it's coming back. Hello, Gray. All right, it seems like we are experiencing technical difficulties. Okay, we will end this if it doesn't come back in a minute. Hello? Yeah, okay, so it's also about time. Sorry, we ended the session with a little bit of a technical issue. But everyone, I would do a big round of claps for Gray's work. Privately, I can't hear you guys, but it's a wonderful talk. We will be back next week with Frederick Krentet talking about LSTM and string flow prediction. And I will be excited to come back again at the same time next Friday. All right, let's see. He's trying to call back in. Let's see if he succeeds.
Hi, sorry about that. Can you hear me now?
Oh yeah, I hear you now.
Sorry, I don't know what happened.
Yeah, we still have 58 audience. It's a big event today. There was almost at one time I think 150 per people online. So it was well
Great.
received. Thank you, Gray. And we were giving you a round of applause privately. So let's take one more question, and then we will end this webinar. How about which one do you want to take? Can you see the questions? You can choose one to take. I'll let you do that.
Me? Are you talking to me?
Yeah.
I have not been watching them.
Okay, so I'll ask this for you. One last question. Gabriel Boris Rami asked, in the final error analysis, were you only looking at the improvements from incooperating observations, or also improvements in combining process modeling with physics-based modeling?
Yeah, that's a great question, and I think that I'll avoid answering it directly, but what we're doing is we're using this procedure here. So we're actually, the model ends up being the original model plus some Gaussian process correction function, right? And the procedure, so the procedure that we're using here, where we iterate between data assimilation and retraining the Gaussian process, that's necessary in order to train the parameters, the free parameters of this Gaussian process model. The Gaussian process, like any machine learning model, has free parameters that we need to optimize. And the question is how to optimize them, given that we don't observe all of the states of the system. So X here is things like storage in the slow flow tank, it's soil moisture storage, storage in the slow flow tank, storage in the quick flow tank. So there's all these state variables that we don't observe directly. We only observe input precipitation, input potential evapotranspiration, the energy term, and output stream flow. That's all we observe. So we don't have enough data to observe this correction factor exactly. So we have to use this expectation maximization procedure, which assimilates observation data in to update the states, and then retrains the model to emulate the updated state corrections, and then it does that over and over and over again. And basically, it ends up with an object that looks like this, where we have a Gaussian process that's added to our dx/dt equation, but that Gaussian process is trained through a process of data assimilation. I don't know if that clarifies, but I think the answer to Gabrielle's question is that I think I'd argue that in some sense it is a combination of physics modeling, which is this thing here, with machine learning, which is this thing here. It's not, I would certainly say it's one of the least satisfying approaches of the ones listed here, but it's the only one that I've had any luck coming up with a way to actually implement it. It's not the least satisfying. I think doing things like regularizing the loss functions is deeply unsatisfying. Semi-supervised learning I don't really know much about, but I think certainly the adding of just the explicit addition of a physics model with a machine learning model is not as satisfying as it would be if we had a way to impose hierarchical constraints on model architectures that were relevant for hydrology problems, and it's certainly not as satisfying as it would be to derive partial differential equations directly from trained machine learning models.
Okay, can you quickly answer Hervé Guillon's work? Question is, he's wondering what the El Nino the performance of the El Nino model presented. How is that related to the spatial and temporal scales of the input data? Why is that performance kind of poor?
Okay, yeah. The temporal scale here is daily, and the spatial scale is point based. So we have no explicit spatial scale. We're doing this separately, this analysis separately for each of these 70-ish sites. I think it's like 69 sites that have enough data to train and test daily networks. And so we're doing it for each site separately. So we're thinking about a point-based system, just a one-dimensional system with a footprint of something realistically like tens of meters, but we don't have any spatial dimension. And the time scale is days. And then these statistics I'm presenting on the left here, which say the fraction of sites where we have statistically significant differences between INSO periods. right? That's just asking what fraction of the sites. So we evaluate each site independently, and then this is plotting what fraction of those sites come up with statistically significant differences. Same over here. This is correlation. So we just take the modeled versus measured deltas at each site, and we just correlate them over sites. So over here, we're saying across the 70 sites, what's the correlation? So to be perfectly, the answer to the question, I think, as I understand it, is the time scale is daily, the space scale is point-based.
Okay, thank you. I actually have a question for CUAHSI. How do people get access to this video, or how to access the slides?
Yes, so we record this session, and then we'll update it on the YouTube site by tomorrow morning.
The YouTube site of CUAHSI?
Yes.
Okay. Okay, thank you.
You're welcome.
All right. Thanks, everybody. That's it. That's a great session. And look forward to seeing you again next Friday. So,
thanks,
thanks, great. So, Ainsley, you may, I think, close this now. Thank you.